Time feels like a river we all drift in, but physics says it is part of a single fabric. That fabric bends, stretches, and sometimes tricks our clocks. When Einstein wrote his papers, he stopped treating space and time as separate stages. He glued them together into what we now call spacetime. The idea feels odd, like merging two colors into one shade. Special relativity tells us that the speed of light is a hard ceiling for any object. If you push a light-year-long ruler close to that speed, its length shrinks for an outside observer. At the same time, the ruler's own clock ticks slower. I find it hard to picture a clock that slows because of speed. Yet the math insists, and experiments with fast particles confirm it. Their decay rates stretch out exactly as the equations predict. Time dilation is not just a lab trick. Your phone's GPS receiver already accounts for it. Satellites orbit Earth at 14,000 km/h, and their onboard clocks run faster by about 45 microseconds each day. If we ignored that difference, your navigation would drift by several kilometers each day. Engineers add a tiny correction before the signal leaves the satellite. That correction is a direct consequence of spacetime's flexibility. General relativity adds another layer. It says that mass tells spacetime how to curve, and curved spacetime tells mass how to move. The wording sounds poetic, but the effect is measurable. Imagine a stretched rubber sheet held taut. Place a heavy ball in the center, and the sheet sags under its weight. A marble rolled nearby will spiral toward the ball, not because a hidden force pulls it, but because the surface itself is bent. Replace the sheet with spacetime, the ball with Earth, and the marble with a passing photon. Light follows the curved paths, appearing to bend around the planet. That bending was first observed during a solar eclipse, confirming Einstein's prediction. Because the sheet bends, distances measured along it differ from flat space expectations. Likewise, the interval between two events, what we call proper time, depends on the curvature. A clock deeper in a gravity well ticks slower than one far away. We experience this every day, though the effect is tiny. A clock on a mountain runs a few nanoseconds faster than one at sea level. The difference comes from Earth's gravitational pull being weaker higher up. These examples show that time is not an immutable river flowing the same everywhere. It is more like a temperature that varies with altitude. Different observers can legitimately disagree about how much time has passed. That disagreement is not a paradox. It is built into the geometry. In spacetime, the shortest path between two events is called a geodesic. For a free-falling object, that path looks straight, even though the underlying surface may be curved. I don't always feel comfortable calling a curved surface straight, but the math is clear. A geodesic minimizes the interval, just as a straight line minimizes distance on a flat sheet. Because spacetime can stretch and squeeze, we can imagine scenarios where a path loops back on itself. Such loops are called closed time-like curves. Their existence would let an object return to an earlier point in its own history. We don't really know whether nature permits those loops. Some solutions to Einstein's equations allow them, others forbid them with additional conditions. The debate remains open among theorists. Even without loops, the malleability of spacetime already lets us travel forward faster than a stationary clock would allow. A spaceship that skims close to a massive object experiences slower proper time, emerging later having aged less. That effect is sometimes called gravitational time dilation. It is the same principle that makes GPS work, only amplified by stronger gravity or higher speed. The math treats both speed and gravity as ways to tilt the spacetime sheet. When we speak of tilting, we must remember the fabric is four-dimensional. We cannot picture it directly, but the rubber sheet analogy helps us feel the idea. The sheet's sag represents curvature in the spatial directions, while the time direction stretches or compresses. If you try to stretch the sheet uniformly, you change the distance between points but not its shape. If you pull it unevenly, you create hills and valleys that affect how objects move. Spacetime behaves similarly, though with an extra time axis. Our everyday sense of time, seconds ticking on a wall clock, comes from a region where spacetime is almost flat. In that limit, Einstein's equations reduce to the familiar Newtonian picture, and time feels absolute. But the moment we look at high speeds or strong gravity, the flat approximation breaks. The clock's tick becomes a variable, responsive to the surrounding geometry. That variability is the key that later ideas about moving through time will exploit. The notion that we could manipulate the geometry deliberately is still speculative. We have no technology to create large-scale curvature on demand, yet the equations do not forbid it outright. Scientists have proposed exotic matter with negative energy density as a possible ingredient for shaping spacetime. Such matter has never been observed, and its existence remains a hypothesis. Even if we could gather it, the amount required to open a macroscopic tunnel would be astronomical. The energy budget would dwarf the output of entire stars. That practical hurdle keeps the idea in the realm of thought experiments. Nevertheless, understanding that spacetime is a flexible medium reshapes how we think about cause and effect. It replaces the idea of a rigid clockwork universe with one that can be stretched, squeezed, and bent. That shift is subtle but profound. It tells us that now is not a universal slice of reality, but a local agreement between observers sharing a similar motion and gravitational environment. When two people meet at a coffee shop, they can agree on the time of their meeting because their world lines intersect. Away from that intersection, their clocks may diverge without any contradiction. I sometimes wonder how many unnoticed differences accumulate in our daily lives because of tiny curvature effects. The answer is probably minuscule, yet the principle remains. In the end, the picture that emerges is one of a fabric that can be tugged, indented, and locally stretched. It is not a static backdrop, but a participant in every physical process. If you look up at the night sky, the light from distant stars has traveled through regions where spacetime has been warped by unseen masses. That light arrives slightly delayed, a hint of curvature across billions of years. Even now, the faint flicker of a distant pulsar's pulse is delayed by a few microseconds as it skirts a hidden galaxy cluster. I sit with a notebook, the kind that records numbers more than stories, and I try to keep the equations straight. When a clock rides on a fast train, its seconds stretch like a rubber band pulled tight. The factor that tells us how much stretch occurs is called the Lorentz factor. Gamma equals 1/square root 1 v2c2. It is a simple fraction, yet it swallows whole worlds of intuition. If the train moves at 3/4 the speed of light, gamma climbs to about 1.5. That means every second on the train feels like 1.5 seconds for a stationary observer. The effect is tiny at everyday speeds, but the math does not lie. I find it hard to picture a minute feeling like 90 seconds, yet the numbers are stubborn. The classic twin story illustrates the point without needing a laboratory. One twin boards a rocket, zips out into space, turns around and comes home. The other stays on Earth, reading newspapers. When they meet, the traveler is younger, his body having ticked fewer heartbeats. The paradox seems to shout contradiction, but the resolution lies in the fact that the traveling twin changed frames, accelerating to turn back. The equations keep the ledger balanced. Acceleration itself does not cause the age gap. It is the high speed that does. The rocket's velocity determines the Lorentz factor, and the factor determines how much the traveler's clock lags behind Earth's. I sometimes wonder whether the twins ever argued about who was right. The math says the traveler ages less, and the data from particle accelerators agree. Gravity does something similar, but it pulls in the opposite direction. A clock deeper in a gravitational well ticks slower than one higher up. Einstein's field equations tell us that mass curves spacetime, and that curvature tells clocks how to run. Near Earth, the difference is minuscule, yet measurable. A clock at sea level loses about 45 nanoseconds per day compared with a clock on a mountain. Those nanoseconds matter when we try to keep time across the planet. The global positioning system relies on satellites orbiting at 20,000 km altitude. Their onboard clocks run faster because they sit in a weaker gravitational field, but they also move at about 14.0 ms, which slows them down via special relativity. The net result is that the satellite clocks gain roughly 38 microseconds each day. If we ignored that, a GPS position would drift by kilometers within hours. Engineers therefore pre-adjust the satellite clocks, setting them to tick slower on the ground so that once in orbit they match Earth time. The system becomes a living proof that both velocity-induced and gravity-induced dilations are real. I have watched the correction tables and the numbers sit there, stubborn and exact, as if the universe were a ledger that refuses to be cheated. Mass energy equivalence, the famous E equals mc2, ties into this picture because mass tells spacetime how to curve, and curvature tells clocks how to tick. A massive object like Earth carries energy, and that energy warps the surrounding geometry. The same equation tells us that to push an object faster, we must pour more energy into it. As velocity approaches the speed of light, the required energy climbs without bound. That climb is why we cannot simply accelerate a spaceship to sea and hop into the future at will. The Lorentz factor heads toward infinity as v approaches c, meaning the energy needed also heads toward infinity. In practice, we run out of fuel long before we see any dramatic slowdown of time. The speed limit is not a suggestion, it is baked into the structure of spacetime. Even light itself respects the rule. Photons travel at sea, but they carry no rest mass, so they do not experience time in the way massive objects do. From the photon's perspective, if such a perspective makes sense, emission and absorption are simultaneous. I don't really know how to phrase that without sounding absurd, but the mathematics insists on it. Experiments with muons produced high in the atmosphere provide another glimpse of time's elasticity. Those particles decay in a few microseconds at rest, yet many reach detectors on the ground because they move near sea. Their internal clocks run slower, letting them survive longer than a stationary muon would. The data line up with the Lorentz factor, reinforcing the idea that speed stretches time. Back on Earth, atomic clocks mounted on fast aircraft have confirmed the same effect. In the 1970s, a pair of hydrogen masers flew around the world on a jet while a twin stayed on the ground. When the plane landed, the airborne clocks were a few nanoseconds behind. The discrepancy matched the predictions of special relativity within experimental error. I still feel a faint awe when I read that report. Gravitational dilation can be demonstrated with a simple tower experiment. Place two identical clocks, one at the base, one at the top, and let them run for months. The higher clock will have accumulated a tiny lead. The difference is on the order of picoseconds per day, but modern optical clocks can resolve it. The observation feels almost like hearing a whisper in a noisy room, barely there, yet unmistakable. All these pieces fit together like a puzzle whose picture is a universe where motion and mass are interchangeable with the flow of time. The equations do not ask us to believe, they ask us to measure. When the measurements line up, we accept that time is not a universal metronome but a variable that responds to speed and gravity. There are limits, however, that keep the picture from becoming a freewheeling fantasy. The speed ceiling at sea prevents any object with mass from ever outrunning its own light. Even if we could build a machine that approached that ceiling, the energy cost would dwarf our current capabilities. We do not yet have a theory that merges quantum mechanics with the curvature of spacetime, so the picture remains incomplete. I sometimes wonder whether a future theory might reveal loopholes, wormholes, for instance, that sidestep the speed limit. Those ideas belong to other chapters, and I must not wander there now. For the moment, the cleanest path we have is the one traced by Lorentz, Einstein, and the handful of experiments that confirm their predictions. In the quiet of a lab, a cesium fountain clock ticks away, its atoms cooled to near absolute zero, rising and falling like tiny beads in a fountain. If we lifted that clock a few hundred meters, its tick would speed up by a fraction of a nanosecond per day. The change is so small that you could not feel it, but the instrument records it faithfully. It is a reminder that even the most inertial of moments is subject to the pull of Earth's mass. The second law of thermodynamics sits at the heart of any discussion about time's direction. It tells us that, in an isolated system, disorder tends to rise, not fall. Take a hot cup of coffee left on a kitchen table. Within minutes, the heat spreads into the surrounding air and the coffee cools. The reverse, steam gathering back into a steaming mug, never happens without external work. That 1-minute cooling episode feels trivial, yet it exemplifies a universal tendency. Each molecule jostles, collides, and shares energy until the whole room reaches a uniform temperature. The number of microscopic arrangements compatible with that uniform state dwarfs the number compatible with the original hot spot. Statistical mechanics makes this clear. The probability of a low entropy configuration is astronomically small. We can write down the equations, but I find it hard to picture the sheer combinatorial explosion involved. When you try to imagine all possible ways 24 atoms could line up, the numbers become meaningless. Because the law is statistical, it does not forbid a brief, local decrease in entropy. A refrigerator, for instance, creates a cold interior by expelling heat elsewhere. But the total entropy of fridge plus kitchen still climbs. Irreversibility therefore emerges from the collective behavior of countless particles. Even if the fundamental laws governing each particle are time-symmetric, the aggregate outcome is not. A single billiard ball bounce can be run backward in a simulation, yet a shattered glass cannot reassemble on its own. The arrow of time we experience, morning turning into night, cause preceding effect, mirrors this statistical bias. Our brains, made of atoms, inherit the same tendency. Neurons fire, memories form, and the pattern of activity spreads, never spontaneously rewinding. Cosmology adds another layer. The universe began in an extraordinarily low entropy state, often described as a smooth, hot plasma. As space expands, the total volume available for disorder grows, allowing entropy to increase without bound. If the cosmos were to contract, some theorists argue the arrow might flip, but we lack evidence. Linking the thermodynamic arrow to cosmological expansion is tempting, yet the connection is not airtight. We don't really know whether the expansion drives entropy increase or merely provides room for it. Observations of the cosmic microwave background give us a snapshot of early low entropy, but the mechanism that set it remains speculative. When we talk about traveling backward in time, the entropy argument becomes a hard wall. To move an object into the past, you would need to reverse the microscopic motions of every constituent particle. That would require an astronomically precise control over degrees of freedom that are, for all practical purposes, random. Some proposals invoke wormholes, tunnels through spacetime that could connect distant moments. Even if such structures existed, the surrounding environment would still obey the second law. A traveler emerging from a wormhole would find the external world still marching forward, its entropy inexorably higher. Consider a thought experiment, a box filled with gas, sealed, then allowed to expand. If we could instantaneously compress the gas back to its original state, entropy would drop. But the compression device would have to consume at least as much entropy as it removes, preserving the overall increase. Quantum mechanics sometimes blurs the picture, offering reversible unitary evolution. Yet measurement, a fundamentally thermodynamic act, introduces irreversibility. When a photon hits a detector, the detector's temperature rises ever so slightly, adding to the entropy budget. Even black holes, the densest objects we know, obey a generalized second law. Their event horizons carry an entropy proportional to surface area, and when matter falls in, the total entropy still climbs. If a black hole were to evaporate via Hawking radiation, the emitted particles would carry away the lost entropy, keeping the arrow intact. The notion of causality rests on the same footing. Cause must precede effect because the cause sets up a low entropy condition that the effect relaxes. If entropy could decrease, the ordering of cause and effect would become ambiguous. In laboratory settings, we can engineer near-reversible processes, such as adiabatic expansions that change temperature without heat exchange. These are useful for testing limits, but they never achieve true entropy reduction. They merely shift it elsewhere. The arrow also appears in everyday friction. A sliding block slows down, converting kinetic energy into heat that spreads into the floor and air. If you watch the block stop, you can infer the direction of time because the heat signature tells a story you cannot reverse. One might ask whether the arrow is an illusion, a product of our limited perspective. Our perception is anchored to memory, records of past states encoded in neural patterns. Those records themselves are low entropy configurations, and they decay as time moves forward. There are speculative models that propose a time-symmetric universe, where two halves run in opposite directions from a central low entropy point. Such ideas are mathematically elegant, but they clash with the observed monotonic increase of entropy in our sector. We lack any empirical hint that a mirror image past exists beyond our horizon. Even if we could isolate a tiny system from its surroundings, quantum fluctuations would still inject randomness. Complete isolation is a theoretical ideal, not a practical reality. The moment any energy leaks, entropy climbs again. The practical upshot for any would-be time traveler is simple. You cannot outrun entropy without paying a cost that dwarfs the benefit. You could, in principle, carry a massive refrigerator along, but the energy required would be astronomical. And the refrigerator itself would generate waste heat, feeding the very increase it tries to suppress. Some researchers explore entropy pumps that use external work to locally lower entropy, akin to Maxwell's demon. The demon's memory must be erased, which, according to Landor's principle, releases heat equal to the entropy saved. Thus the universe's ledger stays balanced. When we look at the night sky, the redshift of distant galaxies tells us space is stretching. That expansion provides fresh room for entropy to rise, reinforcing the arrow on the grandest scale. If expansion were to halt, entropy would still increase, but the ultimate fate of the arrow becomes a subtle question. The link between the thermodynamic arrow and the psychological arrow, our sense of now, remains an open puzzle. Our brains process information in a way that aligns with entropy increase, but the exact causal chain is still under investigation. If a future theory managed to reconcile gravity with quantum mechanics, it might reshape our understanding of time's direction. Until then, the second law stands as the most reliable guide we have. It tells us why a broken egg does not reassemble, why we remember the past and not the future. Even in the most exotic proposals, the entropy budget never disappears. It merely gets redistributed, like a river that never stops flowing, only changing banks. I sometimes stare at a cooling cup of tea and feel the weight of that invisible arrow. The steam curling upward carries away heat, and with it a tiny bit of order forever lost. I sit at a desk strewn with equations, the kind that feel heavier than the paper they're written on. The idea of a tunnel through spacetime has been on the back of my mind for years, ever since Einstein and Rosen first sketched a bridge that could, in theory, link two distant points. Their solution to the field equations looks like a thin tube, an Einstein-Rosen bridge, pinched at each end, a fleeting connection that collapses the instant anything tries to cross it. When I first traced the geometry on a chalkboard, the lines seemed to vanish before my eyes. That is the hallmark of a non-traversable wormhole. The throat closes faster than light could travel through, leaving only a mathematical curiosity. The equations say the bridge exists, but the physics says you cannot survive the passage. It feels like watching a door appear and slam shut before you even reach the knob. A few decades later, a handful of papers suggested a loophole. If the throat could be held open, perhaps a traveler could step through. The term traversable wormhole entered the literature, accompanied by a list of exotic requirements. The most stubborn of these is exotic matter, a substance that would have negative energy density. In ordinary terms, it would push rather than pull on spacetime, a property that seems to run counter to everything we have measured. I find it hard to picture how a cloud of negative energy could be gathered. Quantum field theory tells us that vacuum fluctuations can produce fleeting regions of negative energy, but those regions are tiny and short-lived. The Casimir effect, where two plates create a slight pressure difference, is often cited as a laboratory analog. Yet scaling that up to the size of a human-scale throat feels like stretching a rubber band until it snaps. We don't really know whether nature ever produces enough of this exotic material to keep a wormhole open for any meaningful duration. Assuming, for a moment, that we could marshal enough negative energy, the geometry still demands careful arrangement. Imagine a sheet of paper lying flat on a table. Fold the paper so that two distant points touch. The crease represents the wormhole throat. If you press the 2 points together, the distance between them shrinks to 0 along the sheet, even though the surrounding space remains unchanged. That simple picture captures the essence of a spatial shortcut. The mathematics adds a twist. If one mouth of the wormhole experiences a different flow of time than the other, say, by moving it at high speed or placing it deep in a gravitational well, the shortcut also becomes a bridge between moments. Mouth separation and time shift are the two levers that turn a spatial tunnel into a temporal one. General relativity tells us that clocks tick slower in stronger gravity or at higher velocities. If we take one mouth of a wormhole, accelerate it to near light speed, and then bring it back, the traveling mouth ages less than the stationary one. The throat, if still open, now connects not just two locations but two different slices of time. In principle, stepping through could let you emerge at an earlier or later epoch. The notion of a time-shifted wormhole raises paradoxes that have kept philosophers awake for centuries. A traveler could, in theory, arrive before they left, creating a loop where cause and effect blur. Some physicists argue that quantum consistency would forbid such loops, perhaps by destroying the wormhole as soon as a causal inconsistency arises. Others suggest that the universe might simply allow the loop, but that the probability of any self-consistent history is vanishingly small. I record these possibilities without claiming any of them as settled. The equations do not yet speak with a single voice. Current theoretical constraints tighten the picture further. The energy conditions built into Einstein's equations, particularly the null energy condition, are violated by any configuration that holds a throat open. While quantum effects can breach these conditions locally, a macroscopic violation remains speculative. Moreover, Stability analyses show that even a tiny perturbation could cause the throat to flare outward or pinch shut. Numerical simulations of wormhole dynamics often end with the structure collapsing into a black hole, a fate that seems inevitable without some continuous input of exotic matter. Some recent work explores thin shell constructions, where the exotic matter is confined to a surface surrounding the throat, rather than filling the interior. This approach reduces the amount of negative energy needed, but it also makes the configuration more fragile. The shell must be precisely balanced against the inward pull of gravity. Any mismatch leads to rapid collapse. The math is elegant, the picture tidy, yet the engineering, if one can call it that, remains far beyond any technology we can imagine building. Even if a stable, traversable wormhole could be engineered, the question of how to navigate it persists. The throat would likely be subject to tidal forces, stretching and compressing anything that passes through. A traveler might feel a gentle pull in one direction and a sharp squeeze in another, depending on the curvature of spacetime inside. Calculations suggest that for a throat a few meters across, the forces could be comparable to those near a neutron star's surface. Hardly a comfortable ride. I sometimes sketch the wormhole's interior as a funnel that widens into a second universe, but that image can be misleading. The geometry is four-dimensional. What we draw on a page is a projection that hides the true complexity. When I try to explain the shape to a colleague, the words feel clumsy, and the colleague nods politely while the equations linger on the board. It doesn't quite make sense when you say it aloud. Laboratory analogs have been proposed, using fluids or optical media to mimic the behavior of spacetime around a wormhole. In those setups, light can be guided around a region as if it were taking a shortcut. While useful for visualizing certain aspects, they do not reproduce the requirement for negative energy. They remind me that we can model pieces of the puzzle, but the full picture still eludes us. There is also the question of causality protection. Some researchers argue that a self-consistent solution would involve the wormhole's mouths aligning in such a way that the time shift is exactly cancelled by the travel time through the throat, leaving the net effect null. Others propose that quantum fluctuations would destroy the throat before any paradox could form. The mathematics is intricate, and the conclusions depend on assumptions about the underlying theory of quantum gravity, an area still under construction. In the end, the concept of a wormhole sits at the edge of what our equations can describe and what our experiments can test. The idea that spacetime could be folded, that two distant points could touch like paper, remains an alluring metaphor. Yet the conditions required, exotic matter, precise timing, perfect stability, are all things we have yet to witness in nature. I close my notebook, the last page filled with a sketch of a folded sheet, two circles marked mouth A and mouth B, a thin line connecting them. A stray coffee stain has seeped into the margin, darkening the edge of the drawing. The stain looks almost like a tiny black hole, a reminder that even the smallest imperfections can dominate a delicate structure. The event horizon defines the surface where escape velocity equals the speed of light. Its radius, the Schwarzschild radius, marks the invisible boundary surrounding the singular core. Time near this surface stretches dramatically. A distant observer sees clocks crawl toward stillness. For a traveler, minutes become years, a dilation predicted by relativity. I find it hard to picture a clock slowing because space itself is stretched. Saying it aloud feels odd, yet the math leaves little doubt. Rotating or care, black holes add a twist, literally, to the picture. Their spin drags spacetime around, frame dragging like syrup swirling in a cup. The spin creates an ergosphere, a region where nothing can remain stationary. Within it, particles can gain energy by slipping outward, a process first described by Penrose. The energy gain comes from the black hole's rotational kinetic energy, effectively slowing its spin. The Penrose process shows that rotational energy can, in principle, be extracted. A spacecraft might harvest that energy, though engineering such a feat remains far beyond us. In practice, converting that energy into thrust would require fields far stronger than any we can generate. Inside the horizon, the singularity appears as a point of infinite density. General relativity fails there, so we cannot trust its predictions beyond that point. Some theories replace the singular point with a wormhole connecting distant spacetime regions. Such bridges would collapse instantly unless exotic matter holds them open. Such wormholes, if they exist, would link regions separated by billions of light years. Even a stable bridge would subject any probe to tidal forces that rip it apart. Gravity's gradient near the throat could stretch matter by billions of Gs. The Event Horizon Telescope gave us the first image of a black hole shadow. The bright ring of accreting gas outlines the photon sphere just outside the horizon. Polarization maps revealed magnetic fields twisted by frame dragging, confirming theoretical predictions. That ring proves light can orbit the hole bent by extreme gravity. Its size matches predictions from the Schwarzschild and Kerr metrics. LIGO detects the ripples from black hole mergers, letting us hear horizon dynamics. The chirps encode masses, spins, and the final black holes settling into a Kerr state. These detections also constrain alternative gravity models, reinforcing confidence in general relativity. Waveforms agree with numerical relativity, confirming that horizons behave as Einstein described. Yet no signal escapes from beyond the point of no return, keeping the interior dark. The mathematical expression for time dilation is square root 12 gm/rc2 in the Schwarzschild metric. As r approaches the Schwarzschild radius, the factor approaches zero, freezing external time. This factor directly translates into the rate at which a distant clock appears to tick. From afar, an infalling star appears to freeze at the edge, its light red shifted away. In reality, the star continues inward, meeting the singular core. Quantum mechanics suggests the singularity may be replaced by a finite, fuzzy region. Without a complete quantum gravity theory, this idea remains speculative conjecture. Closed time-like curves appear in the Kerr solution inside the inner horizon. They mathematically allow loops back in time, but physical stability is doubtful. Crossing the inner horizon would expose an object to divergent blue shifts from the external universe. Those blue shifts would flood the interior with high-energy photons, likely destroying any structure. Such blue-shifted radiation would also heat the interior, further destabilizing any structure. Thus, equations permit a path, yet reality probably forbids safe passage. The energy influx alone would tear apart any conceivable probe. We infer interior behavior only through indirect clues like disk flickering and X-ray echoes. These observations let us model spacetime geometry without seeing past the horizon. Temporal reverberations in the X-ray light echo the geometry of the warped region. The accretion disk's temperature rises as material spirals inward, acting like a cosmic thermometer. Its inner edge sits just outside the innermost stable circular orbit, marking the black hole's spin. Higher spin pushes the ISCO closer to the horizon, enhancing frame dragging effects. That shift changes the frequency of quasi-periodic oscillations we detect in X-ray light. These frequency shifts allow us to estimate the black hole's angular momentum with reasonable accuracy. Those oscillations hint that spacetime itself is being twisted by the hole's rotation. Gravity is not just a force, it is geometry we can feel. A traveler near a massive black hole would experience less proper time than distant observers. A round trip could return to a universe decades older. Such a scenario remains purely theoretical, as no probe has yet survived such an excursion. The effect mirrors the twin paradox, amplified by intense gravity. Survival would demand shielding against radiation, tidal forces, and spaghettification. Spaghettification stretches objects into thin strands as gravity pulls more strongly on one end. Near a stellar mass hole, the gradient becomes lethal at relatively large distances. Supermassive black holes, with horizons millions of kilometers across, present gentler gradients. A probe could approach closer without tearing, yet still experience extreme time dilation. Their massive size also means the orbital period of nearby stars can be measured over decades. Astronomers thus favor galactic center giants for studying dilation, as their size softens tidal stresses. Their spin can be measured via X-ray spectroscopy of iron K-alpha line broadening. X-ray timing also captures reverberation lags that map the inner disk's response to flares. Broadening confirms relativistic effects, validating the frame dragging predicted by the Kerr solution. All observations stitch together a picture that matches Einstein's equations to remarkable precision. Yet the singular core remains a blind spot where our physics stops. Some propose quantum effects cause a bounce, turning the singularity into a white hole. If a bounce occurs, it might produce a brief burst of high-energy particles detectable by future telescopes. A white hole would expel matter, perhaps linking to another spacetime region. No observational signature has yet confirmed such an event in the universe. Such an outburst would resemble a gamma-ray flash, but with a distinct temporal profile. Without evidence, the concept stays in the domain of speculation. Black holes nonetheless serve as natural labs for testing gravity at its limits. LIGO's merger detections opened a new window on that laboratory, each chirp revealing horizon dynamics. The final black hole settles into a rapidly spinning Kerr state, its spin defining the size of its ergosphere. The signal's polarization also matches predictions for a rotating spacetime, adding another layer of verification. The ergosphere, unlike the horizon, permits energy extraction without crossing a point of no return. Magnetic fields could tap that energy, a mechanism proposed by Blandford and Zajic. Astrophysical jets from active galactic nuclei may be powered by this process. They shoot out at near-light speed, a testament to black holes acting as engines. Their collimation suggests magnetic fields channel the extracted energy into narrow beams. Even without a portal, black holes let us watch time slow, not reverse. They are extreme playgrounds where relativity can be tested against observation. Observing how clocks behave near these objects continues to test the limits of our theories. The latest horizon image shows a bright spot flickering on the ring's edge. It likely marks a hotspot where magnetic reconnection briefly accelerates particles to near-light speed. The first second after the Big Bang left behind more than a smooth sea of particles. It also left scars, thin, one-dimensional defects that stretched across space like cracks in cooling glass. Those defects are called string-like topological features, and they are predicted by many high-energy theories that try to stitch together the forces we see today. I keep a notebook of the equations that describe them, and each time I look, the geometry around a string feels like a tiny cone cut from a sheet of paper and then glued together. If you walk around the tip of that cone, you do not return to the same angle you started with. The space itself has a missing wedge. The missing angle is proportional to the string's tension, which can be a sizable fraction of the Planck scale. That tiny deficit creates a global effect. Light passing near the string is bent, not by a mass like a star, but by the very shape of spacetime. I have watched simulations where a distant galaxy splits into double images, not because a massive object sits between us, but because a string slices the sky. The geometry is simple enough to write down, yet it hints at a stranger possibility. If two such strings move past each other at relativistic speed, the combined deficit angles can line up in a way that a path through spacetime loops back on itself. In that loop, an object could travel forward, then find its own past self waiting a few seconds earlier. Physicists call that a closed time-like curve, or CTC for short. I find it hard to picture a world line that folds like a ribbon and meets its own tail. A CTC does not need a wormhole tunnel to exist. The conical geometry alone can do the work, provided the strings are arranged just right. The mathematics says the loop closes when the relative velocity and the tension satisfy a precise inequality. In practice, the required speed is close to the speed of light, and the strings must be almost perfectly straight over astronomical distances. That already feels like a stretch, but the equations do not lie. One obstacle is the need for negative energy density somewhere along the loop. General relativity tells us that ordinary matter curves spacetime positively, pulling geodesics together. To keep a CTC open without tearing the fabric, you need a region that pushes rather than pulls. In theory, quantum fields can produce small pockets of negative energy, such as the Casimir effect between two plates. I have tried to estimate how much of that effect would be needed to support a string-induced CTC, and the answer is unsettling. You would need a negative energy density comparable to the string's own tension, spread over a macroscopic volume. That is far beyond anything we can generate in a lab. Even if nature supplies the negative energy, the strings themselves must be stable enough to survive for billions of years. Some models suggest that strings could decay by emitting loops of themselves, which then radiate gravitational waves. The decay rate depends on the string tension and on how tangled the network is. Observations of the cosmic microwave background have been used to place limits on how many strings could have existed without leaving a visible imprint. So far, the data allow only a handful of strings per horizon volume, each with a tension below a certain threshold. Detecting a string directly would be a triumph. One proposed signature is a line discontinuity in the temperature map of the microwave background, caused by the Doppler shift of photons crossing the moving deficit. Researchers have scanned the sky for such line-like features, but the noise level and foreground contamination make it easy to miss a faint signal. I have written a small code that runs a matched filter on simulated maps. The output shows that even a perfect detector would need an improbably bright string to stand out. Another possible clue comes from gravitational lensing. Unlike the smooth arcs produced by massive galaxies, a string would create identical, undistorted copies of a background object, separated by a fixed angle. Several surveys have reported candidate pairs, but follow-up observations usually reveal subtle differences that betray a more conventional lens. The rarity of clean examples keeps the idea alive but unproven. Even if we could locate a string, moving it into the right configuration for a CTC would be a different beast. Strings are not like ropes you can pull. They are anchored by the topology of the early universe. To change their trajectory, you would need to inject energy on a scale comparable to the string's own mass per unit length, which is on the order of 1021 kilograms per meter for the strongest candidates. No known technology can approach that. Some theorists have suggested that collisions between strings could naturally produce the required geometry. In a high-energy collision, two strings might intercommute, swapping partners and forming a loop that briefly encloses a CTC before the loop shrinks away. Simulations show that such events are fleeting, lasting perhaps a fraction of a second in the string's rest frame. Detecting them would require a detector capable of sensing rapid, localized bursts of gravitational radiation, something we are only beginning to imagine. The need for exotic matter also appears in other proposals for time-like loops, such as rotating cylinders or massive shells. Those ideas share a common thread. They rely on stress-energy configurations that violate the usual energy conditions. The energy conditions are not strict laws. They are assumptions that keep the equations well-behaved. When you relax them, the mathematics opens doors to CTCs, but reality may close them with unknown physics. I keep returning to the question of whether the universe simply forbids CTCs in practice. Hawking's chronology protection conjecture suggests that quantum effects would become violent enough to destroy any nascent loop before it could be used. The conjecture is not a theorem, and attempts to prove it have run into technical roadblocks. In my own calculations, I see hints of divergent vacuum polarization near the would-be loop, but the approximations break down before I can claim a definitive answer. What we do know is that the early universe was a hot, chaotic place, and topological defects could have formed as it cooled. If any survived, they would be relics of physics at energies we cannot reach today. Their very existence would tell us that the symmetry-breaking patterns we infer from particle experiments are incomplete. That alone makes the search worthwhile, even if the prospect of a time loop remains speculative. The most concrete hope for evidence lies in the pattern of polarization in the microwave background. A moving string would twist the polarization vectors along its path, leaving a line of aligned angles. Recent experiments have measured polarization with unprecedented sensitivity, yet the statistical significance of any line-like feature is still below the detection threshold. I have plotted the expected signal for a string with tension just below the current upper bound. The curve sits barely above the noise floor, like a whisper in a storm. If we ever manage to isolate a candidate, the next step would be to model its spacetime in full general relativity, including the back reaction of any negative energy fields we might introduce. That is a computational nightmare, requiring adaptive mesh refinement and careful handling of singularities. My colleagues have run a few toy models on small grids, and the results always show the CTC collapsing as soon as the negative energy is switched on. It feels like trying to hold a soap bubble together with a pin. Even the act of measuring could disturb the configuration. The very photons we use to trace a string's path carry momentum, and in principle they could nudge the string's motion. The effect is minuscule, but when the geometry is balanced on a knife edge, any perturbation might tip it over. I have calculated the recoil for a typical microwave photon interacting with a string of moderate tension. The displacement per photon is far below any practical concern, yet the cumulative effect over billions of photons could be non-negligible. In the end, the picture that emerges is one of delicate balances and extreme conditions. A string-induced closed time-like curve sits at the intersection of high tension, relativistic motion, and exotic energy. Each ingredient alone pushes the limits of known physics. Together, they form a structure that feels more like a mathematical curiosity than a physical object we could ever manipulate. Still, the equations do not forbid it outright, and the universe may have hidden such configurations in places we have not yet looked. The latest sky surveys have mapped more of the microwave background than any previous mission. Within those maps, a faint, straight discontinuity appears near a region of slightly higher temperature, a place where a string, if it exists, would have left its mark. The line is only a few arcminutes long, but its orientation matches the prediction for a moving deficit angle. I have marked it in my notebook, a tiny clue that could either be noise or the first hint of a string-like defect. The equations that Einstein left us are stubbornly precise, and yet they hide pathways that look like shortcuts through time. One of the earliest curiosities is the Gödel universe, a solution where space itself rotates like a whirlpool. In that model, every point drifts in a circular motion, and if you follow the flow long enough, you return to your own past. The mathematics demands a uniform distribution of matter with a peculiar pressure-to-density ratio, something we have never seen in the night sky. I find it hard to picture a whole cosmos spinning as a solid body, because every galaxy we observe seems to move independently. Even if such a rotation existed, the closed time-like curves would appear only beyond a certain radius, a region we cannot reach without first crossing a horizon that already contains the loop. The picture is elegant on paper, but the physical ingredients feel more like a thought experiment than a blueprint. A few decades later, Tipler proposed a different construction, an infinitely long cylinder spinning at near light speed. The idea is simple: drag spacetime around the cylinder, and a particle that circles close enough can trace a closed time-like curve. The math checks out, provided the cylinder never ends and its angular momentum stays forever constant. An infinite object is, of course, impossible to build. Any finite version would let the curve unwind before it closes. I don't know any material that could survive the centrifugal forces required to spin that fast, let alone stretch without end. The requirement alone makes the Tipler cylinder a useful illustration rather than a realistic engine. Then came the Alcubierre warp drive, a geometry that contracts space ahead of a ship and expands it behind. The metric is crafted so that a bubble of flat spacetime moves faster than light relative to distant observers, while locally nothing exceeds the speed limit. If the bubble were to loop back on itself, the path would become a closed time-like curve, effectively turning the drive into a time machine. The catch lies in the stress-energy tensor. It demands regions of negative energy density, something that violates the classical energy conditions. Those conditions, null, weak, strong, are the guardrails that keep ordinary matter from behaving oddly. Quantum field theory does allow fleeting negative energies, but the amounts needed for a warp bubble are astronomically larger than any vacuum fluctuation we can measure. So the geometry remains a mathematical curiosity, not a construction plan. Stephen Hawking introduced a safety net he called the chronology protection conjecture. He argued that quantum effects would become violent wherever a closed time-like curve tried to form, destroying the loop before it could be used. In simple terms, the vacuum would generate enough energy to blow the would-be time machine apart. No proof exists, but the conjecture has survived many attempts to find a loophole. If it holds, any exact solution that permits time travel must be accompanied by an instability that renders the solution unphysical. Energy conditions themselves are not absolute. They were formulated before we understood quantum stress. When we relax them, exotic solutions like wormholes and warp drives appear, but they also open the door to paradoxes. A classic paradox is the grandfather problem: travel back and prevent your own birth, which then prevents the travel in the first place. Some physicists reply with self-consistent histories. The universe only allows events that do not create contradictions. That idea sounds tidy, yet it forces us to accept that free will might be an illusion in a spacetime that loops. Philosophers have long debated whether a universe with closed time-like curves can be logically coherent. One argument holds that any attempt to change the past is simply redirected into a different branch of history, but the mathematics of general relativity does not provide a branching structure. Instead, the equations describe a single, smooth manifold where every point has a unique coordinate. If a loop exists, the loop's interior must already contain the outcome of any action taken on it. I don't really know how to reconcile that with our everyday sense of cause and effect. The practical side of these solutions also runs into the problem of sourcing the required matter. Negative energy, if it can be harvested, would need to be concentrated and stabilized, a task that would likely melt any surrounding structure. Even the Gödel universe assumes a cosmological constant of a specific sign and magnitude, which conflicts with current measurements of dark energy. The Tipler cylinder needs a material with tensile strength beyond any known alloy, and a length that would stretch across light years. Alcubierre's bubble demands a pressure gradient that would tear apart any spacecraft that tried to sit inside. All these obstacles point to a common theme. The mathematics is permissive, the physics is stubborn. When we write down a metric that permits closed time-like curves, we are often imposing conditions that no known field can satisfy. That does not mean the equations are wrong. It simply means nature may have additional constraints we have yet to encode. Some researchers suggest that a full theory of quantum gravity would automatically exclude the pathological solutions. Others hold that a deeper understanding of entropy might forbid loops because they would allow information to circulate forever without degradation. We don't really know which of these ideas will survive future experiments. What we can say is that each exact solution acts like a probe, testing the limits of Einstein's theory. They force us to ask whether the field equations are complete, or whether they need a quantum amendment that closes the loopholes. In the lab, we can simulate aspects of these metrics using analog systems, fluid flows that mimic horizon behavior, for instance. Those experiments give us a glimpse of how horizons react to disturbances, but they stop short of producing a real closed time-like curve. Even the most advanced simulations cannot generate the negative energy densities required for a warp bubble. So far, the only place where closed time-like curves appear without exotic matter is in the interiors of certain black holes, such as the Kerr solution for a rotating singularity. Inside the inner horizon, the geometry permits loops, yet any traveler would be crushed by tidal forces long before reaching that region. The inner horizon also suffers from mass inflation instability, a runaway growth of energy that likely destroys the structure. Thus, the black hole route to time travel remains a theoretical footnote rather than a viable path. When we list these solutions side by side, a pattern emerges. Each one trades a physically reasonable assumption for a mathematical convenience. Rotate the universe, stretch a cylinder forever, or inject negative energy. Each step pushes the model farther from what we can observe. The chronology protection conjecture reminds us that nature may have a built-in veto, but we have yet to see it in action. If the veto works, it would appear as a burst of quantum radiation, a flash that erases the region where the loop tried to form. Detecting such a flash would require instruments that can monitor spacetime at Planck scale energies, far beyond our current reach. Until then, the exact solutions sit in our textbooks, beautiful equations that whisper of possibilities we cannot yet grasp. One small detail catches my eye. In the Gödel metric, the coefficient GTT becomes 0 at a radius of about 1.5 times the characteristic length scale, marking the boundary where time-like paths turn space-like and the closed curves first appear. Entanglement feels like a pair of gloves tossed apart, one left, one right, yet each knows the other's orientation instantly. The distance between them can be millions of kilometers, but the correlation survives. When we measure one glove, the other's state snaps into place, as if the act of looking reaches across empty space. I find it hard to picture how information could travel faster than light without breaking relativity. Delayed choice experiments push the puzzle further. A photon passes through a beam splitter, then we decide whether to observe its path or its interference pattern. If we wait until after the photon has been detected, our later choice still determines whether it behaved like a wave or a particle. It doesn't quite make sense when you say it aloud. The future seems to whisper to the past. The quantum eraser adds another layer. We first mark which path information, then later erase that mark, and the interference pattern reappears. It is as if the photon's history rewrites itself when we choose to forget. Wheeler's participatory universe captures this oddity in a single phrase. Observers help bring reality into being. In the lab, a detector's setting appears to shape events that have already occurred. I sometimes wonder whether the universe is less a clockwork machine and more a notebook waiting for ink. At the Planck scale, space itself is no longer smooth. Quantum foam bubbles and fizz, with tiny fluctuations popping in and out of existence. These fluctuations happen on time intervals so brief they are practically meaningless to our senses. Some models of quantum gravity suggest that these foam-like irregularities could form tiny loops in time. Loop quantum gravity treats space as a network of discrete loops, and the same mathematics permits loops that close back on themselves. If such loops exist, a particle could, in principle, travel a short distance forward and then return to an earlier point in its own timeline. The idea of a time loop at the Planck level does not imply a sci-fi time machine. It merely hints that the fabric of reality might not be strictly ordered from past to future. We don't really know whether these loops can be amplified or whether they remain confined to the quantum grain. Entanglement across space-like separation already forces us to accept non-local connections. When we add the possibility of tiny temporal loops, the picture becomes even less intuitive. One could imagine two entangled particles linked not only in space, but also in a subtle, looping time dimension. Experiments have not yet shown any deviation from standard quantum predictions that would require a temporal loop. All results to date fit the mathematics of Hilbert spaces and unitary evolution. Nevertheless, the mathematics does not forbid a tiny retrocausal component hidden beneath the noise. Retrocausality proposes that future measurements can influence past states, but only in a way that preserves overall consistency. In such a view, the universe solves a kind of boundary value problem. The past and future together determine the present. It feels like trying to guess the shape of a river by looking at both its source and its mouth. Some interpretations, like the two-state vector formalism, treat quantum systems as having both forward-evolving and backward-evolving wave functions. The forward wave carries information from preparation, the backward wave from measurement. When they meet, the observed outcome emerges. Loop quantum gravity offers a different language. It quantizes geometry itself, turning areas and volumes into discrete spectra. Time, in this framework, is not a continuous parameter but emerges from the ordering of spin network updates. If updates can form a closed chain, the emergent time could loop back on itself. Such a loop would be microscopic, perhaps a few Planck times long, and would quickly decohere. We lack any experimental handle on that scale, so the idea remains speculative. Open questions linger like dust on a shelf. Can entanglement survive through a Planck scale loop without losing coherence? Do delayed choice results already contain hidden retrocausal signatures that our statistics overlook? The community debates whether a unified theory must rewrite causality or merely extend it. Some argue that causality is an emergent feature, reliable only when many quantum events average out. Others hold that causality is a fundamental constraint, and any apparent retrocausality is an illusion. I often return to the laboratory notebook, where each entry records a single measurement, a single decision. The notes remind me that, despite the mathematics, we are still dealing with concrete clicks and flashes. Even when the theory suggests a loop, the apparatus records a straight line of timestamps. In practice, we test entanglement by separating photons, aligning polarizers, and counting coincidences. The data points line up with the sinusoidal curves predicted by Bell's inequality violations. No deviation hints at a hidden temporal twist, yet the very act of setting up the experiment, choosing angles, timing shutters, feeds into the philosophical puzzle. Our choices are part of the system we study, and that circularity is hard to escape. If quantum foam does contain fleeting loops, they might act like microscopic shortcuts, akin to tiny wormholes. Such shortcuts could, in principle, allow a particle to re-enter its own world line a fraction of a second earlier. The probability of a particle finding such a shortcut is astronomically low, perhaps zero for all practical purposes. Some theorists model these shortcuts with causal sets, where each event has a partial ordering but no global time axis. In a causal set, the notion of before and after is local, not universal. That perspective aligns with the idea that time may be a relational construct, not an absolute river. The experimental frontier pushes toward ever tighter timing resolution, trying to catch any hint of non-standard temporal behavior. Superconducting qubits now operate on nanosecond scales, and their coherence times are measured with picosecond precision. Even with such precision, we have not observed any violation of the standard forward-only evolution. One could argue that the universe protects itself from paradoxes by forbidding macroscopic retrocausality. If tiny loops exist, they might be self-canceling, leaving no trace in the macroscopic world. We don't really know whether the cancellation is perfect or merely statistical. Philosophically, the notion that the future could influence the past shakes the comfortable era we feel in daily life. Our brains are wired to experience cause preceding effect. Any reversal feels like a glitch. Yet the equations of quantum theory are indifferent to the direction we label forward. When I stare at a detector's blinking LED, I sometimes wonder whether the light's flash is already predetermined by a measurement that will happen later. The LED's glow is a concrete, warm pulse, but the underlying quantum state may already contain a future imprint. The search for a quantum gravity theory that naturally includes time loops continues. String theory, loop quantum gravity, causal dynamical triangulations all propose different ways spacetime could be granular. None has yet produced a testable prediction of retrocausal effects. In the meantime, we keep refining Bell tests, delayed choice setups, and quantum eraser arrangements. Each new iteration tightens loopholes, forcing any hidden retrocausality to hide deeper. The data keep matching the standard predictions, stubbornly ordinary. I sometimes feel the weight of these unanswered questions pressing against the lab bench. The equations are elegant, the experiments precise, but the intuition lags behind. It is a quiet tension that settles like dust on a shelf. One small observation remains. The coincidence counter clicks exactly when the two detectors fire within a nanosecond window, no more, no less. Gravitational wave observatories have begun to register mergers that do not fit the textbook binary black hole picture. When the strain pattern twists in an unexpected way, some theorists argue a transient wormhole might have flickered open for a fraction of a second. The detectors themselves are blind to any back-in-time signal, but the waveform carries hints of exotic stress energy that could only arise if spacetime geometry briefly violated the usual causal order. I find it hard to picture a bridge forming inside a black hole collision, yet the data stubbornly refuse to settle into the neat chirp we expect. The current network of LIGO, Virgo, and KAGRA provides a baseline sensitivity that is already probing masses far beyond stellar remnants. If a merger involved a primordial black hole of sub-solar mass, the resulting signal could betray a different merger rate, perhaps hinting at early universe physics that allowed closed time-like curves. The analysis pipelines flag outliers, but the statistical significance remains low. We don't really know whether the anomalies are instrumental glitches or the first whisper of something stranger. High-resolution imaging of black hole shadows offers another angle. The Event Horizon Telescope captured the silhouette of a supermassive black hole by stitching together radio dishes across the globe. The shape of the shadow encodes the bending of light near the event horizon, and any deviation from the Kerr prediction could signal an altered spacetime topology. Recent upgrades have sharpened the resolution enough to resolve structures on the order of a few gravitational radii. Still, the images are smeared by interstellar scattering, and extracting a subtle asymmetry feels like trying to read a fingerprint in fog. Anomalous astrophysical jets provide a more indirect probe. Some active galactic nuclei launch collimated streams that appear to change direction on timescales far shorter than the dynamical time of the central engine. If a jet were to intersect a region where a microscopic wormhole briefly opened, the outflow could be redirected, creating a kink that looks like a sudden, unexplained bend. Radio interferometry can track these kinks, but disentangling them from magnetic instabilities is a persistent challenge. The data sometimes suggest a missing segment of the jet, as if the flow vanished for a heartbeat before reappearing, an observation that keeps me awake. Precision pulsar timing arrays treat millisecond pulsars as celestial clocks, ticking with a regularity comparable to the best atomic standards. By monitoring the arrival times of pulses from dozens of such stars, we can sense ripples in spacetime that pass between us and the pulsars. A passing closed time-like curve would, in principle, alter the light travel time in a way that cannot be mimicked by ordinary gravitational waves. The North American Nanohertz Observatory for Gravitational Waves and its international partners have compiled data spanning more than a decade, yet no clear deviation has emerged. The noise floor is dominated by interstellar medium variations, and I sometimes wonder whether the effect we seek is simply drowned out. Tests of Lorentz invariance add a laboratory-like constraint to the astrophysical picture. If the speed of light were to depend on photon energy, high-energy photons from gamma-ray bursts could arrive earlier or later than lower-energy counterparts, hinting at a broken symmetry that might permit exotic causal loops. Instruments such as the Fermi Gamma Ray Space Telescope have cataloged thousands of bursts, and statistical analyses have placed limits on any dispersion down to parts per billion. The limits are tight, but they do not rule out models where violations occur only under extreme curvature, like near a rotating singularity. Future missions promise to push these boundaries further. The Laser Interferometer Space Antenna will orbit the Sun in a triangular formation millions of kilometers across, listening to millihertz gravitational waves from massive black hole mergers. Its sensitivity to lower frequencies could reveal inspirals that linger in the strong field regime long enough for any exotic geometry to leave an imprint. Meanwhile, the next generation of the Event Horizon Telescope, equipped with additional baselines and higher frequency receivers, aims to resolve the shadow of Sagittarius A** with unprecedented clarity. If the silhouette shows a subtle hole within a hole, that might be the first observational hint of a traversable throat. Each of these programs shares a common limitation. They can only infer the presence of a time travel-like structure indirectly, through the way ordinary signals are distorted. There is no detector that can point at a wormhole and say, "Here it is." The inference chain is long, and every link introduces uncertainty. I often sit with the data plots and feel the weight of that uncertainty pressing against the edge of my notebook. Even with these constraints, the community has begun to catalog null results as valuable as detections. A non-detection of Lorentz violating dispersion, for example, trims away a swath of theoretical parameter space, forcing model builders to tighten their assumptions. Similarly, the absence of anomalous jet bends in a large sample suggests that if wormholes exist, they must be exceedingly rare or too small to affect macroscopic outflows. The silence itself becomes a data point, a quiet that tells us where not to look. One practical step forward is to cross-correlate datasets. If a gravitational wave event coincides with a sudden change in a jet's direction, the coincidence could be more than chance. Coordinated alerts between LIGO Virgo and radio observatories are now routine, but the latency still leaves room for missed opportunities. Reducing that latency to seconds rather than minutes could capture transient signatures that fade before we can point a telescope. Another avenue lies in improving the modeling of the environments where exotic physics might manifest. Simulations of magneto-hydrodynamic flows around near-extremal Care black holes now incorporate higher-order curvature terms that some theories predict. When those simulations produce light curves that match observed variability, they provide a testable bridge between abstract mathematics and real measurements. Yet the simulations are computationally expensive, and the parameter space remains vast. The upcoming square-kilometer array will dramatically increase the number of pulsars we can time, expanding the timing array's sky coverage. More pulsars mean a denser mesh of spacetime probes, which could reveal subtle correlations that a sparser array would miss. The array's sensitivity to low-frequency radio waves also promises to sharpen our view of jet structures, perhaps exposing the faint ghost emission that might linger after a transient shortcut in spacetime. In the meantime, I keep returning to the raw data, looking for patterns that refuse to fit the standard templates. A stray glitch in a strain record, a faint asymmetry in a shadow image, an unexpected delay in a pulse. All of these could be noise, but they could also be the first tremor of a deeper truth. The line between curiosity and speculation is thin, and I sometimes feel the weight of that thinness more than the excitement of discovery. The night sky, when observed through the lens of these instruments, feels less like a static tableau and more like a laboratory in which the fabric of reality is being gently probed. A faint, persistent ripple in the timing residuals of a pulsar located near the galactic plane catches the eye. A deviation of a few nanoseconds that aligns with a weak, low-frequency gravitational wave candidate. The coincidence is tentative, but the data point sits there, unblinking, waiting for a second set of eyes. When I stare at the lab's old clock, I wonder whether any future device could bend its ticks. Time travel feels like a cracked mirror, reflecting both hope and stubborn physics. First, the paradoxes that haunt every proposal deserve a quiet inventory. The grandfather story asks, if you step back and prevent your own birth, what then? It's a simple mental trap, yet it forces the equations to confront consistency. Bootstrap loops add another layer. An object appears without origin, looping forever. Both cases seem to demand that reality either rewrites itself or refuses the change. Physicists have responded with the Novikov self-consistency principle, a kind of built-in safeguard. It says any event that would cause a contradiction simply cannot occur. In practice, that means a traveler might arrive, but the universe nudges the outcome back into line. I find it hard to picture a clock that refuses a hand to move. If such a rule holds, paradoxes lose their bite, yet they remain unsettling. Stephen Hawking offered a different guard, the chronology protection conjecture. He suggested that quantum effects would destroy any would-be time machine before it forms. The idea feels like a subtle pressure, a vacuum trying to keep the fabric smooth. We don't really know whether that pressure is real or merely a mathematical convenience. Even if the universe permits a tunnel, building one would demand technologies we have not yet touched. One speculative route involves stabilizing a wormhole with exotic matter, a substance that resists gravity. Another idea leans on rotating cylinders, the so-called Tipler drive, to twist spacetime. Both concepts sit on the edge of our current theories, where quantum foam meets general relativity. I admit the math feels cold, like metal under a microscope. If a future engineer could harness such forces, the timeline might become a lab bench. That prospect raises ethical shadows we cannot ignore. Changing a past event could erase cultures, economies, even personal memories. Who decides which moments are safe to alter and who bears the responsibility? A single intervention might cascade, turning a minor tweak into a global shift. The principle of non-interference, familiar from other fields, would need a new definition. Legal frameworks would have to grapple with crimes committed before they happen. Even the act of observing a temporal experiment could alter outcomes, a quantum echo of the observer effect. That echo reminds me of the cold metal of a detector, humming faintly in the dark. Beyond the hard science, the idea of moving beyond time pulls at a deeper human thread. Stories of lost centuries and future cities have kept the imagination alive for generations. That cultural momentum fuels funding, even when the equations whisper that success is unlikely. Scientists, like tired watchmakers, keep polishing gears that may never turn. Some argue that the very act of trying expands our understanding, regardless of outcome. I find it hard to picture a future where a single experiment rewrites history. Perhaps the true value lies in the questions we learn to ask. In a lab, a photon flickers, its path measured with trembling hands. That tiny pulse carries a whisper of the universe's tolerance for loops. If a future device could catch that whisper, it might translate into a controlled loop. Until then, the clock on the wall ticks, indifferent to our hopes. I notice the faint vibration of the building, as if the Earth itself sighs. The many worlds interpretation offers a loophole. Each alteration spawns a separate branch of reality. In that view, paradoxes dissolve because the original timeline persists untouched. Critics argue that branching multiplies universes without evidence, turning speculation into metaphysics. Experimentally distinguishing branches remains beyond any instrument we can currently build. Even if branches exist, the traveler would experience only one path, a single thread of consciousness. That raises a philosophical knot. Does consciousness follow the timeline, or does it select a branch? Some philosophers suggest identity is tied to memory, so a traveler would retain knowledge of the original line. If that memory persists, the traveler becomes a living record of a world that no longer exists. The ethical weight of carrying such knowledge is hard to gauge. Would revealing future events accelerate disaster, or could it guide humanity away from pitfalls? We have no precedent, no legal code, only speculative drafts that tremble like paper in a draft. A modest proposal would be to limit interventions to non-sentient systems, such as adjusting planetary orbits. Even that modest step could alter climate cycles, affecting ecosystems that evolved over millennia. Thus, the scale of impact expands faster than our ability to model it. Computational models improve, yet chaos theory reminds us that tiny changes can cascade unpredictably. A single nanometer shift in a magnetic field might, after eons, tip a star's spin. We don't really know whether any such cascade could be traced back to a temporal tweak. That uncertainty fuels caution, but also fuels the stubborn curiosity that keeps labs humming. The practical hurdle of generating exotic matter remains a towering wall of engineering. Current particle accelerators can glimpse negative energy densities, yet only for fleeting instants. Scaling that to a macroscopic stabilizer would demand energy comparable to a small star. Even if we could harness that power, the engineering tolerances approach the limits of material strength. Materials under such stresses would behave like glass under a hammer, shattering without warning. Some propose using quantum entanglement as a communication channel, sidestepping the need for a physical tunnel. But entanglement does not transmit information faster than light, a fact that keeps the idea in the area of theory. It feels like listening to a faint hiss, knowing the source exists but never hearing its words. Even the most optimistic forecasts place a functional time device decades, perhaps centuries, beyond our horizon. That distance forces us to confront the question of why we pursue it at all. Is the drive simply to correct personal regrets, or a deeper urge to test the limits of causality? Personal motives intertwine with scientific ambition, creating a tangled web that is hard to untie. When a researcher watches a clock tick backward in a simulation, the mind registers both awe and doubt. The doubt stems from the fact that our equations, however elegant, are still approximations of nature. Every new discovery reshapes the boundary between possible and impossible, often in unexpected directions. Thus, the future of time travel remains a patchwork of hopeful theory, cautious engineering, and lingering paradox. It is a field where imagination meets the stubborn weight of physical law. I often hear the faint whir of the refrigeration unit, a reminder of entropy's steady push. That push reminds me that any temporal device must fight the same relentless increase of disorder. Perhaps the most honest answer we can give now is that we simply do not know. The clock on the wall continues its tick, indifferent to our theories, our hopes, our doubts. I notice a speck of dust settled on the glass, catching a sliver of amber light.